this is a talk looking at assessing performance of clinical prediction models. And I'm going to be using, just reviewing some of the methods and giving an illustration using breast cancer data sets. But when I was writing the talk, I actually realized that it's probably more useful to actually give recommendations along the way, depending on what data sets you have, what data you have available from the original model that you're trying to validate. And I'll just cover that in this talk, actually. So I'm going to acknowledge some collaborators. So a lot of this work stems from the Stratos initiative, which stands for Strengthening Analytical Thinking for Observational Studies. And it's basically a worldwide collaboration of methodologists, applied statisticians, and other researchers who have an interest in specific areas of statistical methodologies. And there are, I think, 10 different topic groups in Stratos. And I'm in topic group 6, which is on evaluating diagnostic tests and prediction models. So for this particular piece of work, I've been working with some quite eminent names in the world of survival analysis and clinical prediction. So Terry Turno is from the Mayo Clinic in Rochester, Minnesota, and he's written a book on Cox modeling. We've got Ben van Kalster, Laura Wynitz, and Martin van Smidden, and Ewout Steyerberg, all from the Netherlands, and they all have published quite a lot of papers and advice papers on developing and validating clinical prediction models. So it's been a good group to be involved in. So just to give you a quick overview of the talk, I'm going to just cover what are clinical prediction models first. Then I'm going to go into the specific area of prognostic modeling, which involves obviously predicting an event that happens some point in the future. And a common type of statistical model for predicting future events is the Cox proportional hazards model. And then talk a little bit about steps involved in validating a model that's been developed using new data. The methods I talk about, I'll be illustrating using a nice case study on breast cancer patients. And I'll go into some specific methods for the two main kind of assessments that you would want to do when validating a model. That's discrimination and calibration. And then I'll finish with some discussion points and recommendations. So this is a definition of clinical prediction models from Ewout Steyerberg's book. And basically they combine a number of characteristics which can be either related to the patient, the disease under study, or treatment. And it uses that information to predict a diagnostic or prognostic outcome. And I've added in new patients because you've got the data obviously that you use to develop the model. But if this model is going to be used by clinicians in the future in order to help them make decisions on interventions, for example, on high-risk patients, then it needs to perform well in new patients that weren't used to develop the model. Also, they can also be used, such models can be used to manage expectations of patients. Also, the predictions from these models can be used to stratify patients, for example, by disease severity for inclusion in randomized controlled trials. So there are two kind of broad categories of clinical prediction models. The first one is a diagnostic model, which basically is used to predict whether or not an outcome has occurred in that individual at this particular moment in time when the model is applied to the patient. And that traditionally uses a binary regression model such as logistic regression. One example of that is Wells rules, which I can't remember off the top of my head now what that predicts. But the other category which I'm focusing on today is prognostic modeling, which is involved with using information collected at some baseline point in time. So it could be patients just diagnosed with a certain disease, patients who have been admitted to hospital, and it's using the characteristics measured at that point in time to predict their outcome happening in some future time point. So it could be mortality within 3 years, diagnosis in 2 years, whatever. And a popular example is the Q-risk models, which was developed by Julia Hipsley Cox for predicting cardiovascular events within 10 years, I think. These prognostic models are a little bit more complicated because they have what we call censoring. And we're going to be focusing on a particular type of censoring called right censoring. And that can occur by 2 different mechanisms. So because we're following patients up over a certain length of time until they either meet or have some event of interest, or they just get to the end of the study without having the event of interest. Obviously, some of these patients can drop out during that follow-up time. But another reason for censoring is that the patient didn't experience the event at all when the study ended. And that's just called administrative censoring. So, for example, if you've collected a cohort of patients up to December 2020, some of those patients will have got to December 2020 without meeting the outcome. So that's just, they're just censored at that time point because you don't have any information beyond that time. And then, as I said, the other reason for censoring is that they're lost to follow-up. So they perhaps move away somewhere and they're censored at the time point when, they've been lost to follow-up. So one of the assumptions of this is that both types are usually assumed to be uninformative, which means that the patients who are censored are similar in the future risk of an event to those who remain in the study. And that assumption is kind of conditional on the predictors that you've included in the model. So it's essential when you have a developed model, it's essential to validate the predictions from this model to determine whether or not it's accurate at predicting in new patients. So a model developed on a specific cohort of patients will obviously perform pretty well, you'd expect, on that data set that was used to develop it, but it may not perform quite so well in a brand new independent data set when you apply that model formula to the new patients. So it's important to assess how well this model works or behaves in new patients in order for that model to be kind of reliably used to inform decisions in clinical practice. And a lot of guidance exists out there for assessing the performance of logistic regression models, and not so much out there really for assessing performance in survival prediction models, probably because it's actually quite a bit more complicated than logistic regression, where you've only got the outcome is just literally yes or no, did you have an event? Whereas in survival models, you've got this, did you have the event or were you censored over all the follow-up time that you've got. So you've got the added element of time to consider and this censoring issue where they can drop out at some point over that time point. So the aim of this work is to kind of explain the complexities of validating prognostic models and kind of recommend approaches for assessing performance and validating them. And then, as I said, we're going to use a case study which involves developing a Cox proportional hazards model on a data set of breast cancer patients and then validating it on a separate independent data set of further breast cancer patients. So I'm going to, unfortunately, use a little bit of formula here because a lot of this talk depends on a little bit of knowledge on this Cox proportional hazards model, because some of the the way the Cox model is made up, particular part of it, whether or not that particular part is reported in the model, in the paper that developed the model, kind of depends. That has a kind of a bearing on the type of methods you can use to validate that model on a new data set. So the Cox model here is on the right-hand side, and it's made up of two parts. First part I've circled here in red is an exponential term, as an exponential of what we call a PI, and the PI stands for prognostic index, and it's basically, it's made up of this kind of sum of regression coefficients multiplied by the value of their respective predictors. So, for example, x1 may be sex, x2 may be age, and then beta 1 is just the model coefficient for sex, beta 2 the model coefficient for age, and then the PI is just the kind of summation of these terms multiplied together. But you'll notice that from this PI equation that you're missing something that you may see in another model, such as the logistic regression. That's the intercept term, and that's where this H0 of t comes in. And we'll see next that when interest lies in relative risk estimation, you actually don't need to worry at all about this H0 term. So I'll just discuss. So similarly to what you would get in logistic regression, you can estimate odds ratios. You can estimate what we call hazard ratios in the Cox model. So let's just make up some simple models. So say you've only got a Cox model and you've only adjusted for one binary predictor, and just say it's presence of some sort of comorbidity, where yes equals 1 and no equals 0. So you can imagine from this previous slide, if the PI is just beta x, where x is the predictor for the comorbidity. If they don't have the comorbidity, then it'll just be 0. So beta times 0 is 0. So it'll just be e to the power of 0. And then if they do have the comorbidity, the prognostic index will just be beta, because it's beta times x, which is equal to 1. So when you to calculate the hazard ratio, you then just divide the hazard, or divide this kind of equation for patients who have the comorbidity by the equation for patients who don't have the comorbidity. So you get this H0 of t times exponential of the beta estimate for comorbidity, where the comorbidity here equals 1. So that's for patients who have the comorbidity. And you're dividing that by H0 of t times exponential of 0, because these are for patients who don't have the comorbidity. And we're interested in the hazard ratio, comparing the hazard between patients who have the comorbidity versus those who don't have the comorbidity, to find out whether or not people who have the comorbidity are more likely to die during follow-up than those who don't. As you can see, because we're dividing these two, the H0 just simply cancels out, and we're just left with this exponential beta over exponential 0. An exponential of 0 is just 1. So you just got the exponential of the beta estimate for the comorbidity. So that's just maybe a bit of a technical slide just to explain to you that when you're interested in only in the hazard ratios or the relative risk from survival analysis, then you don't need to worry at all about this baseline hazard quantity. But however, because we're interested in predicting the probability of some event happening in the future, we do require the use of this H0 term, because we're interested in absolute risks rather than relative risks. So this H0 term is basically, so like an intercept term in the logistic regression model usually represents the effect of a person with 0 values for the other predictors. So that could be the average person, or it could be the healthiest person, depending on how your predictors have been coded. So for survival models, the intercept will vary depending on the time that a person either experiences the event of interest or is censored. When I say censored, I mean they drop out or reach the end of the study without the event. So instead of intercept, this is called the baseline hazard. And basically this baseline hazard can take this any form at all as a non-parametric quantity. So this is just a graph showing follow-up time, and this line basically represents the kind of hazard of, say, death over each of these time points up to 10 years for a patient who doesn't have, he has maybe all zeros for their predictor value. So it could be maybe the healthiest person in your data set. So it could be like, if you've coded, for example, female equals 0, male is 1, and you've centered maybe on the mean age, it would be the average aged female in the group represented by this baseline hazard. And then because then, and because of that shape of that baseline hazard is similar for everyone, in that previous example, when we calculated the hazard ratio of the comorbidity, say, for example, the hazard ratio for comorbidity was 1.5. That means that the chances of, say, dying was 50% more, basically, for patients who had the comorbidity versus those who didn't. So their shape, basically, of this baseline hazard function here will be similar, but it'll just be 50% higher all the way through the time points because the hazard ratio was 50% greater than patients who didn't have the comorbidity. So that's this assumption comes in of proportional hazards. So one of the assumptions is that this kind of hazard ratio is the same throughout all time points, which may or may not be the case. And there are different methods you can use to adjust for that if it's not the case, but I'm not going to touch on that today. So why is the baseline hazard a problem, really, when you're looking at prognostic modeling? Well, it's necessary for calculation of survival probabilities in new patients. And so the consequences of this are that information on the baseline hazard is not reported in most published reports that use a Cox model. And that's kind of led to a kind of misconception over time that the Cox model does not give estimates of probabilities or absolute risk. Because we're interested in absolute risk, we do need the baseline hazard in order to validate that model on new patients, because it's part of the equation. So I'm just going to leave that for now and go on to a little bit about validation and different types of validation that we can have. So apparent validation is just how well the model performs on the data set that was used to develop the model. So that's kind of a slightly biased assessment because it's obviously going to perform best in that model than it will, sorry, it's going to perform best in the data set that was used to develop the model than it will in any other kind of independent data sets. So it's kind of, it might be useful just to assess how it performs in that, but for use in clinical practice, we really need to validate that model in other data sets. A kind of intermediary validation step is what we call internal validation. This basically involves it's kind of complex procedure, but it involves drawing multiple versions of our data set. Of say you wanted to draw, say, 500 data sets from that data set that we use to develop the models. So say you wanted to develop, to do internal validation, basically we need to draw, say, 500 versions of the data that was used to develop the model from the data set itself with replacement. And then we can use that, it's called bootstrapping approach. And it's kind of like similar to validating a model in the underlying population that was used to develop it. But I'm not covering that one today. What I'm covering is the most important aspect of validation, which is external validation. And that's essential in order to support the application of a developed model on new patients. And it considers patients that differ in some respect from the data set that was used to develop the model. So there might be some slight differences between the two data sets, as you'd expect. And it just shows you, it's a way of assessing how robust it is to slight differences in the population that was used to develop the model. So there are different methods for assessing how well the model predicts in a new data set. And these comprise two important characteristics that we need to assess, and that's discrimination and calibration. And each of these can be assessed separately. I've got overall performance measures up here at the top, but I shouldn't really have included that. That's just really things like R squared, how much variability in the outcome does your model explain. But for external validation, that's not particularly useful. So I'm just going to focus on discrimination and calibration. Where discrimination assesses how good the model is at correctly distinguishing between patients who have the event, i.e. those who are assigned high risk, and those who do not have the event, i.e. are assigned a low risk. So does your model, if you imagine looking at every single pair of patients in your data set, where one patient did have the event, the other patient didn't, did your model give a higher probability to the patient that did have the event than the patient who didn't? And it's basically a fraction of those correctly kind of assigned patients that the discrimination represents. Oh, so yeah, I've got this little drawing. So so basically the red-faced person is someone who actually did have the event, and the yellow-faced person didn't have the event. So I've put a tick beside the top one because for the happy person who didn't have the event, the model predicted their chances of having an outcome as 10%. And for the sad person, it's predicted a chances of 35%. So in that particular case, in that particular pair, the model correctly assigned a higher probability to the person who had the event. And then the bottom one is one where the model has assigned a higher probability to the person in that pair who didn't have the event. So that kind of, in that particular pairing, the model kind of failed to successfully distinguish between those two. So we would kind of do this for every single possible pair in the data set, either the validation or the development data set. And basically the discrimination represents a fraction that the model correctly kind of distinguished between. And then we've got calibration, and it basically assesses the accuracy of the probability estimates from the model across the range of values of predicted risk. So basically what we're doing is, if you imagine a plot of the observed outcome versus the predicted outcome, what you want to see is obviously all these people in your data set lying along that nice diagonal line. If you're getting blue dots quite high up or quite low down, then it means your model's over predicting or under predicting for some patients, and I'll go into that a little bit later. I'm going to skip clinical usefulness for now, but basically there are methods where you, as well as statistical assessment, you need to assess how well it actually can be used to make decisions, but I'm not covering that today because it's just too much to cover. So this is an example. So I'm going to use breast cancer data sets as a case study. So what we're going to do is I've developed a model that can predict what we call event-free survival in patients following surgery for breast cancer. And we're developing that using a Rotterdam breast cancer data set. And it's patients who had surgery between 1978 and 1993. I'm going to use a very predictors, so just number of lymph nodes, tumor size, and tumor grade. So they're all categorical variables. You shouldn't probably, if you things like tumor size where you've got the actual measurement, you probably shouldn't chop it up into categories, but the data sets that we had unfortunately didn't provide the continuous measurement, so we had no choice in the matter. So the outcome I said was event-free survival. What that means is we're looking at the the time from primary surgery to either recurrence, secondary tumor, or breast cancer mortality. So kind of a composite outcome that we're interested in there. So we had 2,982 patients, of whom about 40% had an outcome within 5 years. So we're looking at predicting this outcome within 5 years from surgery. And then for external validation, we're using a separate cohort of patients who had primary node positive breast cancer from the German breast cancer study group dataset, slightly smaller dataset of 686 patients, of whom over 40% had the outcome. I say recurrence, but that should be event-free survival again, like the last slide. Sorry, I'll change that next time. And this basically allows us to assess how well the model performs in this new setting. So this table is our kind of Cox proportional hazards model fitted to the development data sets, the Rotterdam data set. So we've got two columns here. The first one's the hazard ratio for size, number of nodes, and tumor grade. So as an example, if the size of the tumor is between 21 and 50 millimeters, then the hazard of say either recurrence or death within 5 years is 50% higher than the hazard of death or recurrence for those people who have a tumor that's less than 20 millimeters. So as well as having the hazard ratios, I mean, for prediction modeling, hazard ratios aren't particularly useful for assessing performance, but they are useful just for interpretability, so that clinicians can understand, well, what's the effect of all of these predictors on the outcome. What we really want is the coefficients, which is the second or third column in the table, and that's just the coefficients of the model, the beta estimates that I showed you earlier from the Cox model equation. And to get from the coefficients to the hazard ratios, all you do is take the exponential. So it's quite easy to find the hazard ratio. So these coefficients basically represent this kind of PI that I talked about, the prognostic index. So it'd be the summation of this PI equation. You would apply this model to the external data set in order to get the prognostic index of the patients in the new data set using the model that was developed on the development data set. Bit of a mouthful. But what you also need to report, if you're developing a prediction model, a prognostic model using a Cox model, as well as presenting the PI, it's very important to also report the baseline survival. So that H0 function I was telling you about, it represents kind of the intercept equivalent for logistic regression. So I'd actually recommend reporting the baseline survival at all time points, but because we're interested here at 5 years, you really do need to report the baseline survival for 5 years. So here, for example, the chances of surviving up to 5 years for the average or healthiest patient is 0.82. Okay. So moving on now to talk about different ways of assessing discrimination performance in an external data set. So for discrimination, the most common measure that's always reported is what we call the concordance statistic. Quite often, that's the only thing that's reported, unfortunately, for validation. But so a lot of people just look at discrimination and not calibration, but both are equally important. So one of the methods, the most popular method for concordance is Frank Horrell's concordance index. And it's calculated as, so if you imagine, so the denominator for this concordance statistic is basically the number of all possible pairs of patients in which one patient experiences the event at whatever time it was that they had the event, and the other patient did not, i.e. was either censored at that time t or beyond that. That's the denominator. And then the actual Horrell C statistic is basically the proportion of all of those such pairs where the patient with the longer survival time has the lower prognostic index. So basically, it quantifies the degree of concordance as the proportion of such pairs where the patient with a longer survival time has a better predicted survival, basically. And in our case, Harrell C was 0.68 when the model was applied to the actual development data set. But as you'd expect, it was slightly lower, but not too much lower actually in the external data set. It was 0.65. So for perfect discrimination, you'd expect it to be 1, which is basically utopia, never, impossible basically for a model to be 1 or even close to 1. If you get a C statistic of 0.8, that's doing very well. However, Harrell C has a weakness, and it ignores the study-specific ignores the censoring distribution of those patients who were censored before the time t. So what it does, it basically excludes those pairs that I was talking about where the patient who didn't have the event was censored before the time that the patient who did have the event had the event. So there are lots of other alternatives that can be used which do model or take account of the censoring distribution. So for example, one of the most famous ones is UNO's C statistic, and it models the censoring distribution and then uses it to weight the uncensored observations. And it would take too long to kind of go into how to explain weighting, but if you're interested, there's a reference at the bottom. But basically, it kind of adjusts for this weakness that the Harrell statistic has, where it kind of ignores some of the censored observations. And as you can see, the results are very, very similar. So exactly the same for the development data set, slightly lower for the external data set. And that's what you genuinely see, actually. It doesn't really matter what's going on in your data set. All of these discrimination statistics generally tend to agree quite well. And the good thing is about concordance measures, they only really require the prognostic index from the original model for external validation. So you don't actually need the baseline hazard for concordance, which probably explains why calibration is not done very much. So moving on to calibration. So as I said before, it concerns agreement between the observed outcomes and the estimated probabilities of the outcome in the independent external data set. So calibration will often look pretty well in the development data set because you've developed the model in that data set. So really a calibration really needs to be assessed in the external data. And I'm going to talk a little bit about this calibration hierarchy paper, which was written by Ben van Kalster, which is a good paper, explains it really well. Basically, they present 3 different kind of levels to assess calibration. And the first one is this level 1 method, which is just a simple form called mean calibration. And it's just looking at the agreement between the fraction of those, between the observed survival fraction in the whole data set against the kind of average predicted probability in the data set. So what you would want that to be, obviously, is you want those two to be similar. So if you imagine a logistic regression model, to calculate this mean calibration, you would fit that prognostic index as an offset, and then the intercept of that model, just with nothing else in it, is called the mean calibration. But the problem is there is no intercept. Well, there kind of is, but there's no intercept in the Cox model in the traditional like one constant kind of sense. So what do we do there? Well, what we can actually do is a bit of a fudge, and there's a good paper by Crossan et al. Referenced at the bottom of the slide. And what they do is they explain all this in the paper, but the Poisson model is actually very similar to the Cox model. And the good thing about the Poisson model is it does actually have a simple intercept term. And what they do is they transform the what would you say, the predictions basically from the developed model into what we call the expected number of events, and then they fit that expected number of events as an offset in the Poisson model. And then the intercept, again, from that model is the mean calibration. The second level is called weak calibration, and it's defined as having a calibration intercept of 0 and also a calibration slope of 1. So if you imagine logistic regression model, what you would do to get those quantities is you would fit the prognostic index to the validation data set, and then the beta coefficient for that prognostic index would be the calibration slope. And what you want to find is that you want the slope to be 1, because that would indicate that there's no under or over fitting of your model. Basically, there's no, it's not over predicting for some patients and under predicting for others. And again, you can use the Poisson model with the expected number of events as the predictor, and the coefficient again is the slope. So in our actual external data set here, the results are in this little table at the bottom. So the calibration in the large is just another way of saying mean calibration. So what you want this to be is as close to 1 as possible. So you can see there's some slight, so the calibration in the large basically represents, it tells us whether or not there's systematic over prediction or not, or global under or over prediction. So you imagine that kind of curve I showed you with all the dots lying along the diagonal, that's what you want to see. But if you see all of those dots shifting further up or further down, that's global global miscalibration, and that you would, if you see that in the plot, then you would expect this calibration in the large to be significantly greater than 1. And here it's confidence interval it doesn't quite contain 1, so you might suspect some systematic over prediction. And then you've got this calibration slope then, which is actually very good. It's pretty much 1, which suggests that there's not over predicting for some and under predicting for others. And then the third level of calibration is moderate calibration. And that's basically what you want to look at there, is you're looking at among those patients with the same, you want to find, you want to see that the observed risk equals that predicted risk. So that's a bit of a mouthful, but it can be represented on a nice, what we call flexible calibration plot, where you basically plot the predicted probability by, let's say, 5 years against the observed probability of the outcome. And then, as well as just plotting dots, you can actually smooth this plot nicely by modeling these predictions in a Poisson model using restricted cubic splines. So I'll just show you the example. One problem is that the original data set is required for this, which I'll touch on later. So this is an example of a calibration plot. So this is basically, we've applied the model to the external data set and plotted the predicted probabilities along the x-axis and the observed along the y-axis. So the dots here represent 5 groups. We basically chopped our data set up into 5 risk groups, and then we've plotted the average predicted probability against the proportion that we observed to have the event. But in the nice kind of black flexible line, which has these dashed lines either side, the dashed lines are the kind of confidence limits for that black solid line, and that's basically the restricted cubic spline of the fit. And what you want to see is this kind of black solid line kind of overlapping the dot dashed perfect diagonal line of x equals y. So it's kind of agreeing with our intercept here in the table where we had it was 1.14, which suggests there's some under or over prediction systematically, because you see like the dots are all systematically pretty much under the dashed line, so that we've got global over prediction, but the slope here is 1, which makes sense because all the dots are pretty much in a straight line. But the original development data set is required in order to do that form of calibration assessment. And that's obviously not often the case, because quite often you're validating a model that's been published maybe a couple of years ago by a different team. Unless they've made their data set available in GitHub or somewhere like that, or on request, it's not possible to to do that assessment. But there are other ways you can do this. So if the development data that was used to develop a model is not available, you can do that full model validation if the original model paper published the baseline hazard that I talked about for all the observed time points of all the patients that they used to develop the model, plus the prognostic index. So quite often, well, not often at all, actually, it's not very done, but what you can do, some people can publish the baseline hazard at all observed time points as a data set and make it available online so that anyone validating the model on new patients can just download that information and use it to calculate predictions across all time points in their new data set. Another option is to, so this is quite nice actually, I've never done this before, but if the paper that published the original model did publish the Kaplan-Meier curve of the baseline survival plus the prognostic index equation, then what you can actually do this paper by Gaio 2012 talks about you can actually use a digitized to basically the Kaplan-Meier curve, and then you stick it into this package, which then reads that model information and gives you actually quite accurately all of the data points along the Kaplan-Meier curve, and you can input that in along with the PI into your R program or whatever you're using to analyze the data to calculate predictions to do calibration. Another option is if the paper may have just published the baseline hazard for maybe several time points, so maybe at 1 year, 2 years, 3 years, you can, using interpolation, kind of work out, probably slightly the roughest of these three options, work out between those years what the baseline hazard is. Problem is that without having the actual development data, it kind of removes possibility of maybe developing your own model using the original data. That's another different story. If you want to develop a different model looking at different time points, you can't do that if you don't have the original data. So I'm just looking at the time now. But what if you have even less information than that? So if the original model paper only published the baseline hazard at one specific time point, say the time point that they used for prediction in the model that they developed, then you can still do a fixed time point assessment of calibration. I'm not going to go into details of this, but the paper by Austin et al. 2020, which I don't seem to have put the reference up, which is useful. It's a stats and medicine paper anyway by Austin, Peter Austin. They show you how you can actually just use the predicted probabilities at 5 years or whatever time point it is to still do calibration. It's quite similar to the Poisson approach, and it actually does use the Cox model, but it's much more complicated than that, and it would take another hour probably to go through it. It's just to let you know that there are other options depending on what data you've got to hand from the original model. But what if you've got even less information than that? You're really tearing your hair out now. If all you have got available is the prognostic index from the model development paper, then unfortunately you cannot do full calibration assessment. Really the only thing you can do is if the original paper did publish Kaplan-Meier curves for different risk groups. So say, for example, they calculated the predictions for everyone in the data set, and then they chopped it up into quartiles, and then they plotted the Kaplan-Meier curves for each quartile. You could also plot Kaplan-Meier curves of risk of your risk groups and quartiles from your data set and overlay them on top of each other. And if they kind of straddle each other, then it's not full calibration still, but it gives you a little bit of idea, a little bit of kind of reassurance that at least in quartiles the model predictions are similar. In this particular data sets that I used for the case study, you can see that for this top, probably the healthiest risk group, there's quite a bit of difference there between the two. So that's another option, but it's not a formal assessment. So just to finish off then, so there are other measures available that I haven't discussed in this talk that you could explore. There's just a whole vast array of different methods that we can use. I've only published the most popular methods and the methods we're going to recommend in our upcoming paper. For concordance, it doesn't really matter, to be honest, which method you use, but we need an issue. For calibration assessment, you do really need at least the baseline hazard at the time point that you're going to be predicting up to, plus the prognostic index formula. And then just to finish on some recommendations, reporting, discrimination, and calibration, both of those, it's always important when you're validating a model. When reporting a model that you've developed, please help out future external validators of your model by including the baseline hazards for maybe all the time points that were observed in your data set, or at least for a range of time points, because it's essential for proper calibration assessment. And then just to make you aware of the tripod checklists for developing and validation of prediction models. And that's me.